Okay, so we're going to start our next little project here, and this one I've been kind of wanting to do for a while. I haven't built a guitar amplifier in probably about 5 to 10 years. It's been a while. And I decided I want to build a little single-ended guitar amp, and I want to kind of cobble it together from parts that I can find. The goal of this is to make a really good sounding amplifier with as little purchased parts as I can possibly get. Now, of course, you know, resistors, capacitor, things you may have to purchase if I have an odd value, but for the most part, I want to try to use what I have laying around and tailor the design of the amp to what I have. Okay, and it may not be ideal and it may not be a perfect design, but that's okay. Now, when we talked about the other amplifier project we did, the last tube amplifier, one of the things I said was that the design that goes behind guitar amplifiers is different than the design for high fidelity amplifiers. Your frequency range is different. Obviously, a guitar doesn't have the same frequency all the way from 20 cycles up to 20 kilocycles, or 20, yeah. And also, you have distortion is actually a good thing in some instances with guitar amplifiers, whereas distortion in a hi-fi amp is the most horrible thing ever. We never want distortion. We want the cleanest power ever, but different story with that. And we'll get into that a little bit later. The first thing I want to do, and this is our first thing, I found this transformer that's seen better days, but it's a good one. It's just a one-off little orphan, and it's been laying around in my parts box for 20 plus years, and I thought it would be a good exercise to go through with you how to test an unknown output transformer and to find out as much as we can about it. Now, transformers have several things that you need to know about them before you can think about designing an amplifier around them. Okay, so the first thing you would need to know is basically, is it a single-ended transformer or is it a push-pull transformer? Now, normally you can look at the wires and kind of figure that out. If you notice here, we have a red wire and two blue wires. One has a yellow stripe, one is a solid blue, and they're kind of coming off of one direction of the transformer. And then we have three other wires, a black, a yellow, and a green. So we can already kind of guess, we don't know for sure, but we can guess that this little transformer is a push-pull. Red being your center tap for your primary, and then these being your two plate taps for your two output tubes. I can also assume that this black wire would be my common for my secondary, or the speaker output I should say, and that these would be your two impedance taps, which could be 4 ohms and 8 ohms, or 8 ohms and 16 ohms, or 2 ohms and 4 ohms. We don't know. We don't know any of this yet. But we're going to figure it out. Okay? So, how do we go about doing this? Well, actually, it's a lot simpler than you might think. Okay? All you really need is a variac, okay, just a small variac, and you need a couple of, well, even just one voltmeter, but even two multimeters would make it a little easier. So we can handle that. So let's get these out. And what we're going to do, first thing we're going to do, is just determine the turns ratio, or the impedance ratio. Okay, well, first the turns ratio, and then the impedance ratio of the transformer. Now, why is that important? Well, how this reacts to different loads and different voltages and different currents is going to affect what type of tube is going to be best suited to it. Okay, and remember, even though this is a push-pull transformer, at least we think it is right now. You can also use it as a single-ended by using center tap to one of the ends or end-to-end. So there's a whole bunch of different ways we can configure this one transformer to use it with different kinds of tubes, different kind of outputs, and different kinds of loads. All right. So the first thing we want to do, and let me get a little note card here, is we want to determine what we refer to as the turns ratio. All right. Okay. And what we're going to do is we're going to look at the primary to the secondary. Okay? That's how we're going to do it. And by doing this, by putting a certain voltage into the primary and reading the voltage out of the secondary, we can determine the turns ratio. And to make it very simple, I am going to take VP, which is, we don't know what it is, question mark, okay? And we're going to make it 1 volt, okay? And of course, we're going to read RMS volts all the way. So if you read RMS on one side, you got to read RMS on the other side. That's the way it goes, okay? So let's start with that. So the first thing I do is I've rigged this up, and let me get this off. The ring doesn't come off. I'm married and it's kind of stuck on there. I'll be careful. But I've made a very unsafe thing, and I don't recommend this to any of you who are not really familiar with working with electricity a lot. But I basically took a little power cord and I connected a couple of alligator clips to it to make it convenient to connect things up to AC. Now, let me just show you what I'm going to hook it to. As we saw in the shop tour, this is my 1655 variac, isolated variac. And what I'm going to do is, when I turn this on and plug it into the power strip that this is hooked to, I'm going to start with 0 volts. And I am going to start increasing the voltage slowly, and I am going to connect it to this primary. And I'm just going to start by going to the outputs like that, to the plate taps, okay? And we know that the windings to the center tap will be half of what this winding will read, okay? And I'm going to plug this in to the power strip. Then we're going to get a couple of test leads here. All right. So let's grab a couple of these. I'm dropping everything all over the place. Hey, get up there. And we're going to test input versus output. So just keeping it simple. So this will be our input, and I'm setting it to AC volts. All right. And once I get this plugged up, I'm going to go ahead and make sure you can see the displays on all this. So let's put that there. Get rid of all the glare and everything. And then we're going to take our output, and we are going to go, and I am just going to randomly pick one of the leads here. Let's start with the green one. We're going to have to test them both. Okay. Okay. So, here's our primary, here's our secondary. Turn on our meter. And let's make sure that this is saying AC volts. Okay, and it is. Can you all read that? Okay. I'm going to shut this overhead light off a little bit to make it a little easier to see. There. How's that? Looks good to me from here. Okay. So I'm going to turn on the 1655. And as you can see, there's just a little residual 1 volt going on there. And here's what we're going to do. We're going to turn this voltage up on the primary until I get 1 volt out on the secondary. So let's do that. Okay, you can see it going up. We're just taking our time. You got to wait for your meter to settle a little bit. All right. Here we go. That's about 1 volt. I would say 0.999, within 1 millivolt. And you can see I have 30.5 volts in. So right now my ratio is 30.5, I'm sorry, 30.5 to 1. Okay? Now we have to write down here, let me move this very carefully. We want to write down here that this is to the green lead. Okay? So the green lead is 30.5 to 1. Okay, that's our turns ratio. Now, I'm going to shut this back down. I'm going to move this over to the yellow lead. Okay. I'm going to repeat my test. Okay. Okay. Right there, I would say roughly. And it looks as if I'm getting about, we're going to call it 22 to 1. Now it's not, you're not going to be dead perfect, but it's going to be very close, within 1 turn. And that's going to be the yellow. Okay, let's turn that down. All right, we're done with that for now. Okay, so let's disconnect this and get these things out of the way for the moment. Okay, everything's unplugged. Turn everything off. Some room to work. Okay, so basically we've got our turns ratio. So for green and yellow. All right. And so for green, we know that the turns ratio is 30.5 to 1. Okay. And to calculate the impedance ratio is going to be your turns ratio squared. So if we take our calculator and we say 30.5 times 30.5, that's 30.5 squared, our impedance ratio, I, equals 930.25 to 1. All right. Now, what does that mean? That means that we're assuming that this is a 1 ohm load. Okay, 1 volt, 1 ohm, 1 amp. Okay. If I want an 8 ohm load on here, then I times both sides by 8. So for 8 ohms, my primary impedance will be that times 8, or 7.442K. All right. Does that make sense? So that's going to be your primary impedance with an 8 ohm load, okay, provided that your speaker is presenting an 8 ohm load. Now, speakers are not a resistance. Speakers are a reactance, okay? They are an inductive reactance. So what that means is, as the frequency is changing and as the properties of the signal are changing, its reactance back, reflecting back through this transformer, are changing with it. So that means your 8 ohm speaker does not always put an 8 ohm DC load on your amplifier. Okay? It gives a variable load, but it averages around 8 ohms. So that's where we test it at. So basically, this would be a 7.4K load if we use this as a single-ended transformer, okay, with respect to the two outside, so in other words, you have your primary looks like this, right? So you got the two blue leads here and the red lead here, okay, you see that? And from here to here will be an 8K or 7.4K load on your plate of your tube. We're ignoring this one. Now, of course, that's going to change with our turns ratio. If we're looking, and that's your plate to plate, okay? If you want to just look from center tap to a plate lead, it's going to be half of that. So you got to go all the way back to here. It's going to be 15 to 1, which is 15 squared, which, so everything's going to be lower. But that's what we're looking at for right now. Now with the yellow lead, okay, your turns ratio is 22 to 1, right? Our impedance ratio is 484 to 1, right? Which, at an 8 ohm load, 3872. Okay? So what you're finding out, the yellow is a lower ratio than the green. So green is probably going to be what they consider your 8 ohm tap. And the yellow is probably what they're going to call the 4 ohm tap. Okay? So this would have a 4 ohm and an 8 ohm output. Okay? And that's how you figure out the information about your transformer. Now there's a lot more that goes into this transformer than just the turns ratio and the impedance ratio. So, for instance, the type of core material that they use, the type of iron, the type, whether it's ferrite or solid iron or whatever, this has a certain thing called permeability. Permeability is the ability to magnetize and demagnetize, okay? And how you make this will determine how well this transformer can perform. So some of the more expensive transformers use a more expensive type of core material. They also will use larger amounts of core material. So the bigger the iron, the more magnetism you can create, the better that the transformer will perform to a certain point. Okay? Transformers with little iron that are little tiny will lose their magnetism, will saturate. They call that saturation. They will saturate more quickly. Okay? The type of iron also will affect the frequency response. So some of these transformers can have a pretty flat signal all through the hearable range of 20 cycles to 20 kilocycles. Okay? That's hard to do. It's very hard to find a core material and a winding ratio and so forth that will keep a nice flat response curve. But it can be done. Very expensive transformers. Most of them kind of taper off on the ends. At the lower end, they kind of drop off a little bit, and the higher end, they kind of drop off, and they try to design them so that the mid-range part of it, they try to stay flat with the frequency response. Okay? So I would imagine this came off of a hi-fi device, but I don't know for sure. It could have been off of an old guitar amp. I don't really remember. It's just a really long time ago I had this. But regardless of what it is, it's a decent size, and typically something of this size and this amount of iron, this would typically look like anywhere from a 10 to a 20 watt transformer. Somewhere between a 10 and 20 watt amplifier. And again, when you look at the impedance ratio and you look at the plate impedance, let's take a look at some other stuff now. So here's a tube sheet that I just had, alright, that I was looking at, and it is for a type 6550 vacuum tube, which 6550s are pretty big tubes. Those are, you know, these are for 2 tubes can make a 100 watt amplifier. Okay, but let's look at what we're interested in. That's why I printed this one. For Class A, single-ended, single tube, the load resistance, see what they're talking about? Your load resistance. Depending on the voltage that you're putting into it and how you bias it, that load resistance is different on that tube. Okay, so if we run 400 volts on the plate of the tube, okay, DC plate voltage, it's saying that your load resistance, the resistance that this tube will appear to have, like if you had, in other words, this tube will act like a 3000 ohm resistor when it's biased this way with 400 volts. Okay? Now, here's the trick. This transformer should have an impedance that somewhat matches this tube. The further away from that you get, the more stress that you're going to put on your tube, because the tube needs to have that kind of resistance reflected back upon it. If not, at certain frequencies, it will cause the tube to draw excessive current, and it may even exceed the limits of the tube. On the other hand, if the resistance goes too far the other direction from this 3000 ohms, it could not cause the tube to bias enough, and the tube will start clipping or distorting or saturating early. In other words, you're not getting the full power capability of the tube because most of it's being absorbed resistively. So while it is possible to put a tube onto a transformer where the two impedances do not match, it's not desirable because it is going to put flaws in the design of your amp. Now, that being said, this is a guitar amplifier. This is where things get a little bit crazy. Sometimes people will tend to mismatch them on purpose to cause the amplifier to distort. That distortion changes the sound of that guitar, sometimes in a desirable manner. It will create that sound that you just can't get if you plugged your guitar into, let's say, a very clean, low distortion, high fidelity amplifier. Okay? Now they may do it at the expense of the tube. Some tube amplifiers purposely do this and purposely will cause the life of the tube to be shortened. Some guitarists or musicians do not care about the life expectancy of the tube. All they care about is the type of sound that it produces. So they're willing to sacrifice that, and they understand that every so often, you know, maybe every 3 months, 6 months, year, whatever, they're going to have to replace the tubes in the amplifier because of that. Okay? And it's something they're willing to do. It's an expendable item. Now, if you design your amplifier properly, tubes can last many, many years. Okay? But that's a matter of preference and choice. So anyhow, basically what I came up with, here's what I originally did on this transformer. And I tested it and came up with very similar numbers to what we saw just now. Okay, as you can see, 3872, 3872. Okay, almost perfect. On the green lead, I came up a little bit different. okay, and that's going to the center tap. And 7442, I came up 7488. I probably read my voltage a couple of tenths of a volt different, but that's okay. But you can see how it came out. And what I came up with was, if I use the outside tap of the transformer, all right, so I used the two blue wires, and I went with the yellow lead and an 8 ohm speaker on the yellow lead. But wait a minute, I thought you said it was a 4 ohm tap. Well, it's all about what load you put on one end and what load you put on the other end of this transformer. It's dynamic. That's why this tap doesn't read 8 ohms. As a matter of fact, 8 ohms is the impedance. It's the reactance that it reflects back to the load. But when you look at this, what do I got? Can you see that? Half an ohm. That's all we're getting. So the DC resistance of this has nothing to do with 8 ohms, 4 ohms, anything. It's a half of an ohm. And if this were a different transformer with a different core material and a larger winding and larger diameter secondary winding wire, it may be different than that yet and still be an 8 ohm winding. Okay? It's all about reactance. Okay? So basically, the formula for this would be, if I used a 6550, and I'm not going to be driving it too hard, and I put about, we might want to go a little over 400 volts. If we increase the voltage a little bit, all of this would change, and this resistance would go up a little bit. And I use the yellow lead, okay, 8 ohms to the yellow. I would find out that this is going to be just a little bit over 3K ohms, 3872, okay? So maybe about 410 to 420 volts, and this would be right, almost a perfect match. Okay, you seeing that? I'm pointing to things and I'm not even on the camera. Here we go. See? So between 410 and 420, this would be a little higher. Yellow lead with an 8 ohm load. This would work for a single-ended 6550 guitar amplifier. See how I came about that? Now, other tubes have different plate characteristics, and they may not match up this way. Like a 6L6 was a little bit different than this one. Okay, 6BQ5 was a lot different. And actually, this amp probably either was designed for a 6BQ5 or a 6V6 push-pull. Okay, because they have a little higher plate resistances and so forth. They're a little different. But regardless, this should work for this. Okay? So I hope that helps you understand a little bit about an output transformer. It's not as simple as it sounds, and I know when you look in a catalog at transformers, they only really give you two functions usually. They just tell you what the output impedance is, and they tell you what the input plate impedance is. And that's really all you need to know if you're shopping a transformer, because you just buy the combination that you want. The only exception to that is there are transformers called universal output transformers, and they have 5 or 6 wires on the output, and they're not marked any ohms at all, and maybe 5 or 6 wires on the input, and they're not marked with any resistance or any impedance at all. And then they come with a chart, like a sheet of paper, and it'll say if you connect this combination of wires on the primary and this combination on the secondary, it will be this plate resistance and this impedance of speaker. So you basically follow the little chart and wire it the way they say, and it will turn the transformer into whatever type of transformer you want. And there's no disadvantage to those universal transformers other than extra wires, and usually they cost more because of the extra wiring they do in them. But other than that, there's nothing special about them. So just understand that whenever you're picking a transformer and you don't know anything about it, the first thing you want to do is connect your power supply up to it, a variac, move to the primary, to the plate side, and you want to drive that voltage of the plate until you get a 1 volt output. And that's going to give you your turns ratio, or your voltage ratio of the transformer. From that, you can calculate everything else that you need to know. So that's lesson number 1 here for our tube guitar amplifier. Now, somewhere down here, I think, yes, I have, and I need to test it, but I knew I had this laying around. It's an old power transformer, and I think this may have come off of an old TV that I stripped or something, I don't know. But anyways, I think this will give me that 400 whatever volts that I need. And again, we can actually make this voltage whatever we need, because I can either, if I need higher voltage than what it is, I can use diodes for my rectifiers. If I need to lower the voltage a little bit, I can choose different types of vacuum tube rectifiers that have voltage drops in them. So like a 5U4 will have a voltage drop of, maybe 30 volts. So it'll knock 30 volts off of that, off of my DC. So anyhow, we'll get to that later. But we have 2 transformers, so we have the beginnings of our amplifier. Now the next thing we're going to do on our next lesson is we're going to try to come up with some sort of a schematic that will fit what we have here. And again, my goal for this project is not to make the perfect ultimate amplifier. If I wanted to do that, I'd spend thousands of dollars and buy all the top shelf, perfectly matched, absolutely perfect parts, and I'd build it. Okay, so anyways, that's what we're doing, and we're going to move on from here, and I'm going to end this video right here, right now. And like I said, the next thing I think we need to come up with is some sort of a schematic. And just like the first one, we're formulating a recipe, we're experimenting, and I'm sure whatever the first drawings is not going to be what the final drawing is going to be. And I'll do this all on camera so that you can see all the mistakes that goes with it, and they're not even mistakes. Again, unless you're really good at engineering and you're really good at design engineering and can calculate things perfectly, and the constants, in other words, there's no variables, every last detail about the transformers and every detail about the tubes and every detail about every little thing, you really cannot calculate everything right out. Sometimes it's a little bit of trial and error to get it how you like it, and there's nothing wrong with that. That's part of this hobby. That's what makes it fun, is that you don't know. You're learning, you're experimenting, and you're coming up with something new that's your own, that you've done. And now, of course, you want to build a second one, you have the recipe. You've formulated it. But for that first one, it's going to be a lesson learned each thing you do. And that's the part of it that I like. I'm very pleased with the way that amplifier turned out. And it sounds really good, especially with the right preamp connected to it. And I'm sure this one's going to turn out the same way. It'll be a lot of fun. So, and I really hope you guys can follow along and do something similar. Maybe you'll want to go online maybe, or find some old gear and tear the transformers out and maybe build your own too. Now the next thing I'm going to show you also, after we get a schematic, is a real easy way to make a chassis if you don't have a lot of woodworking or metalworking materials. I'm going to show you a crude design that works really well, and I'm going to do that on purpose. to show you that you don't have to have the best metalworking skills or the best tools, or you don't have to buy a prefabbed chassis that costs, you know, 50 bucks or 100 bucks. You can make something just out of some sheet metal, some sheet aluminum. So, all right, more to come. Again, thumbs up if you like what you see, and as long as I have the time to do it, we'll keep going. All right, thanks a lot. Till next time.